In lesson 9, we finally were able to factor the sum of perfect squares. Because we have these complex numbers now, we can now say, wait a minute, I can now factor over the sum of perfect squares by extending into the complex field. So, for each equation, determine the real and complex solutions. So if I have x to the fourth minus 1 equals 0, well, the first thing I said, well, wait a minute, that's the difference of perfect squares. That's x squared minus 1 times x squared plus 1 equals 0. But I can keep on factoring because x squared minus 1 is the difference of perfect squares. But this x squared plus 1 is a little bit different. It's the sum. And in class we said, well, wait a minute. That's really x squared minus negative 1. Look at that. Minus negative 1 is x squared plus 1. So what two numbers multiplied together gives me x squared? X times x. Well, what's the square root of negative 1? Minus I and plus I. So that factors as x minus I, x plus I equals 0. So what are my solutions? We get x equals plus or minus 1 from the real, those are my real solutions from the first two terms, and x equals plus or minus I from those second two terms. Those are my four solutions to this equation. We can now factor the sum of perfect squares by saying it's basically the difference of perfect squares, but I'm going to stick an I on to deal with the plus. Let's see here. I've got four terms, which means I'm grouping. X squared times x minus 3. I better end up with x minus 3. I'm going to have to take out a 25. Well, my new GCF is x minus 3 from those two terms, so once I GCF that out, I'm left with x squared plus 25. And before today, we would say that can't be factored. But we now say, wait, that's the sum of perfect squares. We can factor that as x plus 5i and x minus 5i. It's basically the difference of perfect squares, except there's a complex number. There's that imaginary unit involved. So my solutions are, I have a real solution of x equals 3, and then I have two complex solutions of negative 5i and positive 5i, so plus or minus 5i. Those are my three solutions to that equation. X squared plus 4, well, I can now factor that as x plus 2i, x minus 2i, and x squared plus 16, that's x plus 4i, x minus 4i, and it's equal to 0. And using the zero product property, I get four solutions. I get x equals negative 2i, x equals positive 2i, so I'm going to write that as plus or minus 2i, and I get x equals negative 4i and positive 4i, plus or minus 4i. Those are my solutions to this equation. This equation only has complex imaginary solutions. If p of x equals this polynomial here, state all solutions to p of x equals 0. So I want to know what are the solutions to this equation. Well, I've got a trinomial here, so I'm going to factor it by asking myself, what multiplies to negative 27 that adds to 6? What two numbers multiply to negative 27 that adds to 6? 9 and negative 3. But in the front seat, I need an x squared because it's a trinomial. It's a trinomial in x squared, not plain old x. So when I factor x squared plus 9, I can factor that over the complex numbers to find all real solutions to get x plus 3i, x minus 3i. And I can treat x squared minus 3 as the difference of perfect squares. I don't need complex numbers here because it is a difference, as x plus the square root of 3 and x minus the square root of 3. So my four solutions are x equals negative 3i, x equals 3i, x equals negative radical 3, and x equals positive radical 3. Don't be afraid to have square roots in your difference of perfect squares. X squared minus 3 can be factored over the real numbers if we have the square roots there, which is why we need the real numbers. And again, you could write this as plus or minus 3i, plus or minus radical 3. Both work. Find the solutions to this equation in a plus bi form. So I'm already telling you you have complex numbers, so don't even try factoring it because you know the solutions are complex. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So cleaning this up, I've got 6 plus or minus the square root of 36 minus 40. Type the discriminant into your calculator. Get negative 4 over 2. But wait a minute, the square root of negative 4 is 2i, because the square root of 4 is 2, and the square root of negative 1 is I. So my solutions are 3 plus or minus I. So the zeros, my complex zeros here are 3 plus I, and x equals 3 minus I. So how does this help me factor it as the product of linear factors? So, if I told you you had a 0 at negative 2, you would say x plus 2 is a factor. If you had a 0 at 7, you would say x minus 7 is your factor. So, if I have a 0 at 3 plus I, my factor is x minus 3 plus I. If I have a 0 at 3 minus I, my other factor is x, the opposite of that, minus 3 minus I. If I was to multiply those two expressions together, I would end up back at x squared minus 6x plus 10. So we can use the quadratic formula to get our zeros and use that relationship between the zeros and our factors to be able to factor really any polynomial over the complex numbers in this way.